What happens when a star, after burning for millions or billions of years, finally runs out of fuel? This is not just a question about a distant point of light. It is a question about the very engine of cosmic creation and destruction. The stars that illuminate our night sky are not eternal flames. They are vast, dynamic nuclear reactors, engaged in a constant, delicate balancing act. Gravity relentlessly pulls their immense mass inward, seeking to crush them into oblivion. At the same time, the nuclear fusion in their cores generates tremendous energy, pushing outward and holding that collapse at bay. For most of a star's life, these two forces are in perfect equilibrium, a cosmic stalemate that allows the star to shine steadily for an almost unimaginable length of time. But this balance cannot last forever. The hydrogen fuel that powers a star's core is a finite resource. When it begins to run low, the outward push from fusion weakens, and gravity starts to gain the upper hand. The star enters its final dramatic chapters. Instead, the death of a star is one of the most spectacular and transformative events in the entire universe. The path it takes depends critically on one single factor: its mass. The answer is a story of immense power, profound change, and incredible beauty. The first major stage in a star's demise begins when the hydrogen fuel in its core is depleted. For its entire main sequence life, the star has been fusing hydrogen atoms into helium. But when that core hydrogen runs out, the fusion furnace sputters and goes out. Without the outward pressure from fusion, the core begins to collapse under its own immense weight. As it collapses, it heats up dramatically, becoming far hotter than it ever was. This intense heat ignites a shell of hydrogen fusion in the layers just outside the core. This surge of energy pushes the star's outer layers outward with irresistible force. The star begins to swell to an enormous size, growing hundreds or even thousands of times larger. As the surface expands, its energy is spread over a much larger area, causing the surface temperature to drop. The star's color shifts from a brilliant white or yellow to a deep, ominous red. The star has now become a red giant. In approximately 5 billion years, our sun will begin its transformation into a red giant. Its expansion will be so vast that it will swallow the orbit of Mercury completely. Venus completely. It may even expand far enough to engulf Earth itself, boiling away our oceans. During this phase, the sun will also begin to lose mass, shedding its outer layers in a powerful stellar wind. For low and medium mass stars, including stars like our sun, the end of their life is a process of serene dissipation rather than violent explosion. Once the star has exhausted its helium fuel in the core, its nuclear furnace shuts down for good. It simply does not have enough mass and therefore not enough gravitational pressure. In a series of thermal pulses, it begins to gently puff away its outer layers. These expelled layers of gas, enriched with elements like carbon and oxygen, expand outward in a beautiful glowing shell. This expanding cloud is illuminated by the intense ultraviolet radiation streaming from the hot, exposed core left behind. The result is one of the most beautiful objects in the cosmos, a planetary nebula. At the heart of every planetary nebula lies the remnant of the star's core, a white dwarf. A typical white dwarf might contain about half the mass of our sun, but compressed into a volume roughly the size of Earth. A single spoonful of white dwarf material would weigh several tons on Earth. This extreme density is the result of a quantum mechanical phenomenon known as electron degeneracy pressure. A newly formed white dwarf is incredibly hot, with surface temperatures exceeding 100,000 degrees. However, with no internal source of energy, it is essentially a dying ember. Over billions of years, it will gradually cool and dim, its color shifting from white to yellow to red. Eventually, it will cool completely and become a cold, dark ball of carbon and oxygen, a black dwarf. In that quiet ending, the echoes of their lives continue to shape everything we know. The lives of massive stars are dramatically shorter and more violent than those of their smaller cousins. They burn through their fuel at a ferocious rate, living fast and dying young. As they age, they build up a core of iron, the ultimate ash of nuclear fusion. Unlike lighter elements, fusing iron atoms together consumes energy rather than releasing it. The outward pressure that had supported the star for millions of years vanishes in an instant. Gravity, the relentless force that has been trying to crush the star its entire life, finally wins. In less than a second, the iron core catastrophically collapses inward at incredible speeds, reaching up to a quarter of the speed of light. The infalling outer layers slam into this newly formed super-dense object and rebound. The shock wave is supercharged with energy from a flood of ghostly particles called neutrinos. This explosive rebound is a Type II supernova, one of the most energetic events in the universe. In the moments of this explosion, the star briefly becomes as luminous as an entire galaxy of hundreds of billions of stars. The extreme conditions trigger nuclear reactions that create all elements heavier than iron. Gold, silver, platinum, uranium, every atom of these elements was forged in a supernova explosion. The star scatters these newly forged heavy elements across the galaxy. This expanding cloud of debris will cool and mix with surrounding gas and dust. These remnants are not just relics, they are seeds that will enrich the next generation of stars, planets, and perhaps even life. If the core's mass is between approximately 1.4 and 3 times the mass of our Sun, a truly extraordinary object is formed, a neutron star. The pressure is so intense that it forces electrons and protons to merge, forming neutrons. The entire core becomes a single gigantic atomic nucleus composed almost entirely of neutrons. A neutron star contains more mass than our Sun, yet compressed into a sphere only about 20 kilometers in diameter, roughly the size of Manhattan. A single sugar cube's worth of neutron star material would have a mass of about 100 million tons. Its surface gravity is hundreds of billions of times stronger than Earth's. The neutron star spins at incredible speeds, often rotating hundreds of times per second. This rapid rotation concentrates the original star's magnetic field, making it trillions of times stronger than Earth's. This intense magnetic field generates powerful beams of radiation that shoot out from the neutron star's magnetic poles. Because the magnetic poles are not aligned with the rotational axis, these beams sweep across the cosmos like a lighthouse. If one of these beams sweeps across Earth, our radio telescopes detect a regular pulse of energy. These rapidly spinning, beaming neutron stars are known as pulsars. The regularity of their pulses is so precise that they are among the most accurate clocks in the universe. Neutron stars are extreme laboratories for physics, pushing matter to its absolute limits. The discovery of pulsars in 1967 was a landmark moment, providing first evidence for neutron stars. They remain among the most fascinating objects in the cosmos, the city-sized cinders left behind by the universe's greatest fireworks. If the remnant core weighs more than about 3 times the mass of our Sun, then not even the immense pressure of packed neutrons can withstand gravity. There is no known force in the universe that can halt the collapse. The core is compressed into an infinitely dense, zero-volume point, a singularity. This singularity is surrounded by a region of space-time so warped that it becomes a one-way street. An object has been created from which nothing, not even light itself, can escape, a black hole. The boundary of this region is called the event horizon, not a physical surface, but a theoretical border. Once anything crosses the event horizon, it can never communicate with the outside universe again. We cannot see a black hole directly. Instead, we watch as stars orbit a patch of empty space at incredible speeds. Matter forms a rapidly rotating accretion disk, heated to millions of degrees by friction. This causes the disk to glow brightly in high-energy wavelengths like X-rays. Powerful magnetic fields can channel matter into colossal jets blasted away at nearly the speed of light. These jets can extend far beyond their host galaxy. At the center of nearly every large galaxy lurks a supermassive black hole with mass millions or billions of times that of our Sun. These behemoths play a crucial role in galaxy evolution, regulating star formation throughout the galaxy. Black holes are fundamental architects of the universe. The death of the most massive stars is intimately linked to the life and growth of the largest structures in the cosmos. The death of a star, whether gentle, fading, or violent explosion, is never truly an end. It is a transformation. When a low-mass star sheds its layers, it enriches space with lighter elements like carbon and nitrogen. When a massive star explodes, it forges and flings heavier elements throughout the galaxy. The oxygen we breathe, the iron in our blood, the silicon in rocks, all were forged in stellar furnaces. We are made of star stuff. The history of the universe is written in our own biology. Looking up at the night sky is like looking back at our own cosmic family tree. The faint light from distant stars and nebulae tells the story of our origins. Our own Sun will follow this path in the distant future. In about 5 billion years, it will swell into a red giant. It will shed its layers as a planetary nebula and leave behind a cooling white dwarf. Life on Earth will not survive this transformation, but the atoms that make up our planet will be returned to the cosmos to become part of new stars, planets, and perhaps new life. The death of a star is not an ending to be feared, but a process of renewal to be understood. It is the mechanism by which the universe endlessly reinvents itself, ensuring that even in darkness and destruction there are always the seeds of new beginnings. Even our own sun will one day die, becoming a white dwarf, but not for another 5 billion years. Until then, we continue to be part of this magnificent cosmic story, children of the stars, witnesses to the universe's endless capacity for renewal and wonder.